Hello and welcome back to the Cracking FAANG YouTube channel. Today we're solving Leetcode 26, remove duplicates from sorted array. Given an integer array num sorted in non-decreasing order, remove the duplicates in place such that the unique elements appear only once. The relative order of the elements should be kept the same, and return the number of unique elements in nums. Consider the unique elements of nums to be k to get accepted, blah blah blah. Okay, whatever. Basically just need to reorder the array. So let's look at a basic example here. And let me just write out the array that we want to work with. So we'll do 1, 1, 2, 2, 2, 3, 4, and 5. So as you can see, we have some duplicates here, right? Obviously, this one is a duplicate, this one is a duplicate, and this one is a duplicate. So in theory, our new array should just be 1, 2, 3, 4, 5, and we can get rid of all of this extra stuff. But unfortunately, we don't actually return the array. We basically return the pointer to like where in the array we'd want to cut off from. So in this case, I believe we would return, so this is 0, 1, 2, 3, 4. So I think we would either return 4 or 5. I need to check the problem, but basically it's either 4 or 5 because that's the index, at which case after we kind of perform the getting rid of the duplicates, which would contain the duplicates. So to the left at that point is the unique elements, and to the right is actually the duplicates. So this problem, in theory, sounds quite easy, but it's quite tricky to actually implement. And the way that we're going to do this is we're just going to walk through our array from left to right, and we're going to be checking elements as they come. And what we're going to check is basically, does an element equal to its previous element? If it does, then that means that we have a duplicate, and we should update a pointer. So we'll just call it P, and this is going to point to the location of the last duplicate. So P will tell us location of last dupe. And then as we continue to traverse to our array, so for example, we'd start here because we're going to be checking the previous one. So obviously we can't check outside of the bounds. So then when we get to the 2, we'll see that, okay, 2 is different from 1. So obviously these two are unique. And what we're going to do is we're going to put the value of this new unique element at whatever P is to replace it. So that way we're basically getting rid of this duplicate. So now the array would basically be like 1, 2. And then we'd go to the next one. And then our kind of new insertion index would also go up. So we would basically move our pointer up, since now P is pointing at this one. And it's no longer a duplicate because we swapped it with a 2. We just need to move it forward. So now P would basically move to this index. And now we're processing this 2. Since this one equals this one, basically we can just keep moving forward because we know it's the same, and P is already pointing at the position of the last duplicate. So then when we get to this one, again, we don't have to do anything here. We still know that the last kind of duplicate position was this one. Then we'll get to the 3. We'll notice that 3 is different from 2, which means that we can now swap the 3 with whatever the last duplicate was, which, if you remember, is now this index, which is index 2. So we can swap it, and then we can move along, and then we can move our position up by 1 again, because now that we've replaced this index, it now becomes this next one. So this is now the position where the next unique element should go. Sorry. And then we'll get to the 4, and obviously 4 is different from 3, so we need to swap it with wherever the last position was that we can put in, which, remember, is now this index. So we'd put it here, and we continue on with our processing. We get to 5, and we can see that 5 is different from 4, so then we need to move it up. So now that we've inserted the last one here, now the next unique position is this one, this 2 here, and then we basically swap the value here. We don't care about swapping it backwards because we only care about the unique elements. And now that the array is finished, basically we would just return where kind of the last position was, and that means that everything to the right of it will get chopped, which is what this problem is doing. It's a bit strange. So that's basically the algorithm in a nutshell. It's a bit complicated, especially for an easy problem, but to kind of summarize, we're just going to go from left to right over the array. Obviously, we're going to have one pointer which tracks our current position in the array. We'll call this I, and then we can have a pointer P, which basically is the position of where the last duplicate was, or where we should insert our next unique element. So this is kind of like insert next unique at P. And then every time we see basically a duplicate and we insert an element at whatever P used to be, then we can move P up one by one, and we can keep this going such that at the end we'll kind of have our our final solution. So it's a bit convoluted, especially like on paper. It doesn't really make too much sense. This is one where you have to really kind of just look at it a few times, and for an easy, it's definitely a bit tricky. But let's actually go to the code editor, type this one up, and hopefully it should make a little bit more sense when we're looking at the code. All right, so let us code this up. Remember that we basically need to keep track of kind of 2 pointers here. The first being our pointer as we go through the array, which we'll get for free from our for loop. And then we need to keep track of where to actually insert something. So in my example, I called it P for the pointer, but we're just going to say that we're just going to call it the insert index to use a little bit better names here. And it's going to start at 1 because obviously the first element in the array will always be unique. So we don't have to worry about replacing it because it's the first one. It's always going to be by definition unique. Now what we want to do is we want to basically loop over our nums from left to right. So we're going to say for I in range starting from 1, obviously, because obviously the first element is always unique. We don't have to worry about it. And also we're going to be looking for the element at I minus 1. So if we start at 0, then, well, in Python, we'll just wrap around to the end of the array. But in other languages, you might get a out of index error. And we're going to do length of nums. Now what we want to do is we want to check whether or not we actually have a unique element. If we do, we want to put it at whatever the insertion index is. So we're going to say if nums of I minus 1 doesn't equal to nums of I. So basically if 2 elements next to each other are not the same, then that means that they're both equal. So they're not equal, so therefore they're unique. So we want to basically put whatever number we're currently at in this insertion index. So we're going to say nums of insert index is going to equal to nums of I. Cool. Now what we want to do is obviously now that we've inserted something at this insertion index, we don't want to overwrite what's there. We just need to move it up by 1. So we're just going to say insert index. We're just going to increment it by 1. So that way the next position is now eligible for insertion. And that's really all we have to do. This will kind of replace the elements as we go along. And all we have to do at the end is just return the insert index, because now that, insert index, because now that will just point to the position where we actually want to insert the last element. So let's just run this, and looks like we are good to go. Cool. Accepted. All right, so time and space complexity. This one's pretty straightforward. All we do is we go through the entire nums here. Obviously, in the worst case, actually, you have to go through the entire thing. Anyway, there is no worst case. You just go through everything. So it's just going to be big O of n, where n equals num items in nums, right? Pretty straightforward. For the space complexity, we are doing everything in place. We're not creating any extra variables other than this pointer, but that's just a constant space allocation. So our space is just big O of 1. Anyway, hopefully you enjoyed this video. Like I said, it's a bit tricky, especially for an easy. This one is not the simplest one to kind of think about, especially kind of swapping those indexes and how it works. I think it's probably more of a medium, but whatever. We still have the solution. The code itself is really simple, just coming up with how to do this. It's a little bit convoluted. Anyway, that's enough rambling. Hopefully you enjoyed the video. If you did, why not leave a like and a comment? Helps out with the YouTube algorithm. Subscribe for more content, and I will see you in the next one. Bye.